So as we just saw, using a function approximator, a parameterized function approximator, parameterized, they mean that it has some parameters that we can tune in order to have the relevant output, the output that we would like to have. We saw that this is a pretty powerful tool. But the question is, how do we train it? How do we train the parameters to output what we would like it to output? So let's assume that each state is a vector of features, right? Some high-level features. We'll call them F1 to Fn, n different features. For instance, Pac-Man location, ghost location, food location, and so on. Or even screen pixels. And you might say, well, that's a lot of features, but later we'll see that we can even learn from these features. These are very low-level features. But we can also learn to make sense out of those. And I'll show you some approaches later on. So let's just, for the sake of this example, let's assume some high-level features like Pac-Man location and ghost location, and stuff like that. Then a parameterized value approximator might look like, well, anything that takes the features, somehow scrambles them and provides you with an answer. Not scrambled, makes sense of them and provides an answer. So for instance, you can take all of your tunable parameters, or one tunable parameter per feature, and just sum the multiplication of each feature with its affiliated weight, affiliated theta, affiliated parameter. Right? This is also known as dot product of two vectors, right? The theta vector and the f vector and the feature vector. If you do the dot product, this is the output of a linear approximator. This is a linear approximator. But you can think of any other type of approximator. For instance, Fourier transformation is a possible approximator, or even a deep neural network is a function, can be a parameterized function approximator, right? You give it the feature vectors, it multiplies them by some weights and biases, and it outputs a value. A function approximator, as long as we can, not as long as, it is a function approximator. The question is, how do we train, how do we tune these values to output the correct output, the output that we would like to see. So assume that we have some training data, assume that we know the true value for a set of states. We've observed these states and we know the values affiliated with them, and we would like to train our approximator accordingly. And the question is, how can we update theta, or tunable parameters, to reflect this information? So one approach would be to use gradient descent. So let's say that we have these values and we want to set theta such that for every state, the approximation value, the approximation that we're trying to predict for each state, will be accurate, will be the same as provided to us in the training data for each one of these states. So doing that tweaking the tunable parameters to actually have the same output, the output exactly the same as the output that we expect, that's not generally possible. Why?
Because it's an approximation?
Yeah, we have some limitation on our approximation function. Although some approximation functions are what's called universal function approximators. But we'll discuss that later on. Meaning that they are able to predict with up to an arbitrary error, as low as you'd like it. But in most cases, we have some limited approximation models, approximation functions. For instance, a linear approximator will not be able to approximate a curve. I mean, it cannot, right? So you will have an error. So usually what we want to do is to reduce the error as much as we can, given our approximation limitation. Right? Instead, we'll try to minimize the error, or commonly known in machine learning as the loss function. For our case, we can just say it's just the summation of the error per state value estimation. Okay, so we'll just try to minimize the summation of these errors per state, per one of our 3 states that we have here. So in order to do that, in order to compute to minimize the loss, we'll take gradient descent step. We'll compute the partial derivatives of the loss with respect to each one of our tunable parameters, right? Theta I, each entry in the vector of our tunable parameters. And this partial derivative means how can we change theta I such that the loss will increase the most. Of course, we would like to take, this is just the definition of a derivative. Of course, we would like to go the other way. That is, we'll take a gradient descent step. We'll take a step in the other direction. Now, the way that we define loss will not be able to take the gradient with respect to that loss function, because absolute value is not differentiable. We cannot compute the gradient in a specific location. Which location?
The minimum.
The zero, right? Yeah, yeah. Around 0. It's not the derivative is not defined for absolute error, right? Absolute error looks something like this. Well, here it's not differentiable.
It's at the minimum value, not necessarily 0.
No, you're right. I mean, the error is 0.
Slope is 0.
No, so the slope is not defined at that location. When right, I can't say at 0, but when this is 0, whatever your
derivative is. This is the slope.
Okay.
This derivative is the slope, right?
Right.
Yeah, so the slope.
The derivative is not defined when the error is 0.
Correct.
Okay, so but in machine learning there's a simple fix here where we use the squared loss function instead of the absolute error loss. So commonly we do that. There also is a way to change the loss function for to still use absolute error loss, and in some cases it is useful. Actually, we'll discuss it later on when we discuss deep neural networks and different loss functions. So the absolute error is known as the L1 loss. We simply need to define the derivative where it is undefined. That is when the error is 0. So as I said before, a simple fix would be to use the squared loss function that is differentiable everywhere. Okay, so let's say that we are using the squared error loss, and now the way we train, or the way we perform gradient descent on our function approximator, V hat here, is as follows. For each I, for each tunable parameter, we push theta I, each one of our tunable parameters, towards a direction that minimizes the loss. Okay, and now with the squared error loss, we can compute the partial derivative with respect to any theta I. So more generally, of course, we can do it over the entire tunable parameters, the entire vector of tunable parameter, theta, when we take the gradient. And the gradient is simply this symbol here, which is just a vector of all partial derivatives. And usually we do it as a vector operator for computational efficiency, for increased efficiency. And of course, as we've seen previously, in this case, when we update our function approximator, we use a specific learning rate. The learning rate requires tuning per domain. As we've seen before, when we discussed Q-learning, for instance, too large of a learning step might cause divergence in learning, while too small of a step results in slow learning or even premature convergence. So we have to set the learning rate correctly. Usually this is done empirically. We observe the results or the training curve and tune alpha accordingly.